Assalamualaikum warahmatullahi wabarakatuh. We're from Group 7, Section 1. We will present about group assignment, control system BAV 30503. So this is our group members. We have Muhammad Alif HANIF bin ROSMAT, Muhammad Amiruddin bin HASROLNIZAM, Muhammad AZLY bin AZAHARI, and Muhammad HILMAN HAKIMI bin YUNUS. So we proceed to the preface. For the preface, the speed control of DC motor shows that we can handle and control the speed of as our desired. One of the most useful aspects of a DC motor is speed control. So why we need to know about the speed control of DC motor? Commonly, speed control in the machine has an effect on the motor rotational speed, which has a direct impact on the machine operation and is critical for its performance and output. As a result, one should think about DC motor speed and several forms of speed control approach. Next, we proceed to the introduction. For the part of the introduction, there are various types of speed control for DC motor. One of them is a proportional integral derivative, which is PID. PID controllers are currently the most well-known controllers utilized in industrial control system. The proportional gain, integral time constant, and derivative time constant are three parameters that must be specified when designing such a controller. The creation of a speed and direction motor for an autonomous race robot is discussed in this work is displayed. The PID control algorithm is used in both controllers. As we will see later, the PID control KP, KI, and KD, or we will know as KP, TI, and TD, parameters can be tweaked to produce a variety of response curve from a single process. So we proceed to my other teammate for the literature review.
Thank you, Ame, for the good intro and preface. Now I'll proceed for literature review. So we're able to find 10 literature review that are related to the project from several articles in the internet. So the 10 articles that we found are the design and implementation speed control system of DC motor based on PID control and MATLAB simulating by Salman Hamoudi that published on March 2020. Second, the performance study of enhanced non-linear PID control applied on brushless DC motor by A.M. Abdul Ghani that published on June 2018. The third is speed control of spreadly excited DC motor using class A chopper by Sahana M. Sachin that published on October 2018. Fourth, speed control of DC motor using conventional and adaptive PID controller by Sarah and Al-Barghouti that published on December 2019. Fifth, DC motor speed control using PID controller by Fatiha Luchif that published on June 2019. 7. Speed control of DC motor using optimization technique based on PID controller by Santosh Kumar Suman that published on 2016. 8. CS-based optimal PID controller design for induction motor speed control system by Chayo Tamarat that published on December 2019. And number 9. And number 8, fractional order PID controller design for speed control of DC motor by Vishal Mehra that published on December 2020. And number 9, PLC-based PID speed control system by Avinash P. Kaldate that published on March 2017. And finally, the last, which the turning method of PID controller for DC motor speed control by Ashwaq Abdul Lami, that published on August 2016. So, the literature review from all these articles that are related to the project, which explain the details of the PID controller design for speed control system. It explained the theory, technique, and concept of the project. So that's all from me. Thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ilman bin Yunus. So now I'm going to continue with problem elaboration. So first, our methodology is we do some lectures about PID controller and DC circuit in control system, and then we do the introduction and literature review, and then we find all the components that need to be in the system. Then we derive the numerical model and block diagram for system using MATLAB, Simulink. And then we take all the result and put it in table, discuss the result, and we get result that we get and put it in the report. And then we make the video explaining the simulation finding. After that, we make conclusion for this project and we make video explaining the report. So now for the mathematical modeling, as you can see, here is the parameter for the DC motor. You can see the rated motor terminal, moment of inertia, moment of inertia, load and rotor, motor viscous friction constant, glacial friction for the blade, automotive EMF constant, motor torque constant, electrical resistance, and electrical inductance, rated motor speed, and the input is right. Okay, after that, okay, now we move to the first problem, which is we need to model a DC motor using MATLAB Simulink. So now okay, now as you can see, here is the modeling for our DC motor. You can see here is the electrical part and this is the mechanical part in this subsystem. So after we run, we get first we put for 900 RPM and we get the result here. Okay, after that, okay, for the next problem, we need to implement the diagram for system MATLAB Simulink, which is we already did. Then we run the system and we get the scope here. This is for 900 RPM and this is for 1500 RPM. Okay, then we need to determine the PID gain manually. So for manual PID gain, we tune and here is the gain we get. So for P, we get KP is 83.33 and KI and KD is 0. And for PI, we use 75 for KP and 11.36 for KI. And for PID, we use 100 for KP, 25 for KI and 1.3 for KD. Then we create the control system block diagram for manual tuning PID control on MATLAB Simulink. Okay, and you can see here is the modeling for the manual PID. So we put here 100 for KP and this is for KI and this is for KD for derivative. Then after we run it, we can check the system here. You can check the system. This is the system, which is the blue line for the subsystem and the yellow line is for the input. and then we implement the PI and PID controller using PID gain from table 1. Then we get all the result here. So this is for PID, MPI and PID for 900 RPM. And this is system without controller, which means there is no PID, open loop. And here is for 1500 RPM for PI and PID. And also for no controller. Okay, then next we need to create the system block diagram for automatic finding tuning PID controller on mallet simulink. So what we must do is we need to use the PID controller block diagram instead of using manually like this. So we need to set it for PID. We tune it. We tune it here. And as you can see here is from the PID block diagram. So what this block diagram do is we can automatically set get the gain for P, I and D by determine our favorable response. So we just need to adjust here for response time and transient behavior. So we adjust it. Until it look similar to stable. This actually look very stable to me. So then we update the block. This is just for example. We update the block, then we exit here, and then we get our new gain here from this block diagram, from this PID block. Okay, after that we need to develop the table for comparing PID controller gain for manual and automatic. So our manual is we use 120, 25 and 1.3 for KP, KI and KD. And for automatic, we basically just get it from the PID block. So here we get 4.84, 5.31 and 0.523. Okay, now, and then we plot. We need to plot the comparison between PID controller response for manual and auto. And then we need to minimize the maximum overshoot for less, no more than 10%, and our rust time, settling time, plus minus 5%, and our peak time and error, steady state error from the system response without controller. So we need to create a scope for manual and auto. So we put all the system to this scope. So this line is basically for input. This is for manual, and this is for automatic. So we run it. After that, we can compare all the graph here. So we can see for input, is 1500 RPM. So now let's see for manual. You can check here is overshoot is 0.134%. So there is no overshoot. And actually the rise time is pretty quick. And we can see here there is less steady state error. Then we compare it with our auto tuning. You can check here there is 0.5 overshoot. This is the overshoot, and the rise time is very slower than the manual. So we need to adjust it again until we get our desired verbal response. And after that, okay, now for the problem execution and result, we can see here is for the manual tuning for P, PI, and PID, and system without control. So we can compare the system response here. This is for 900 RPM, and this is for 1500 RPM. So we go through here, and after that, this is for automatic tuning using tuner app. So we can check here is for P using P is 98.33, and this is for PI. We can check again here. P is 23.56 and I is 4.47. And then we can check here PID. We get P is 1.773, I is 2.128, and our D is negative 0.079. Okay, I think that's all from me. I will give next to Muhammad Alif. Thank you.
Okay, my name is Muhammad Alif ROSMAT. Thanks to Hilman for the great explanation on simulation and execution. Okay, for the conclusion, according to the simulation results, a proportional controller KP will reduce the rise time and will reduce but never eliminate the steady state error, whereas an integral control KI will eliminate the steady state error but may make the transient response worse. A derivative control KD will improve the transient response by increasing system stability, reducing overshoot and reducing undershoot. Okay, scroll. Okay, this is for our reference. We get it from the literature review and from introduction and to help the simulation also. Okay, that's all the report from us, group 7. Thank you and Assalamualaikum warahmatullahi wabarakatuh.